Hi, my name is Riley Innes, and this is a pre-recorded presentation for the 2021 meeting of the Australasian Mathematical Psychology Conference. Today, I'll be discussing a new R package developed by a team of researchers at the University of Newcastle called PMWG. PMWG, or Particle Metropolis within Gibbs, is a sampling algorithm for Bayesian Hierarchical Modelling. The method was originally developed by our collaborators David Gunawan and Robert Cohn in their 2017 paper, and more recently was applied to the LBA in a paper with Scott Brown, Guy Hawkins, and Ming-Yong Tran. These papers are linked in the YouTube comments section. From this collaboration, a team at UON, which includes myself, JP, Gavin, Caroline, Guy, and Scott, developed an R package to enable broader use of the sampling algorithm. Now, in psychology and within math psych, as will be evident at this conference, cognitive models are pretty widely used. In recent years, as computational resources have increased and more software has become available, the amount of literature based on cognitive models has grown substantially. These models relate to decision-making, categorization, learning, memory, attention, and more, and are now highly important to psychology as they enable tractable explanations of these cognitive processes. So computational cognitive models provide explanations of these processes through careful parameterization, where the mathematical model parameters link to underlying cognitive processes. And there has been significant research dedicated to showing the selective influence of such parameters. From these models, using probability methods, researchers make inferences about cognitive processes and group differences. This is often done by comparing competing models and selecting the model that best describes the data, or by assessing posterior parameter estimates to see how parameters change across conditions or vary between groups. So the thing is that these methods both require quite precise estimation of the model. There are now many estimation methods such as AMPC, Gibbs sampling, or Hamiltonian Monte-Carlo, and many packages that enable these sampling methods. However, with more complex models, obtaining reliable and stable marginal likelihood estimates that are needed for these methods is quite tricky. So evidently in psychology, there's often greater value in hierarchical models. However, these models are difficult to estimate, and so if posterior samples from these models are imperfect, then our model selection and model inference suffers. Often this is the case with random walk samplers for hierarchical models, which tend to suffer from really high autocorrelation of parameters, as well as slow and uncertain convergence. This is where the PMWG method comes in to sort of solve this problem. Before I explain the method, it's important for me to define some key terms. So here, when I talk about parameter values, I mean the group level parameters. When I talk about random effects, I'm referring to individual subject level parameter estimates. And when I talk about particles, I'm referring to a single vector of parameter values. So if a model has 4 parameters, a particle will have 4 values. PMWG samples on values on the real number line. This is needed for the unconstrained multivariate normal and full covariance structure. The marginal density given from PMWG is the posterior density of the parameters and the random effects combined. Because of the sampling approach, PMWG converges more reliably. Because of the particle sampling approach, PMWG converges more reliably and is more statistically efficient than other hierarchical sampling methods, such as DE, MCMC. And finally, the output from PMWG can be used by model selection methods such as DIC, thermodynamic integration, bridge sampling, or another new method we're currently working on, importance sampling squared. So how does PMWG work? There are 3 key stages, beginning with burn-in and adaptation. Burn-in gives the sampler some throwaway iterations to reach a reasonable posterior space. And then in adaptation, we try to capture enough good samples to create a conditional distribution, which is used in the final sampling stage. So for the sampling algorithm, we first begin with start points, which can be reasonable or sample from the prior. We then sample the population level parameters, that is the mean and the variance with some added variance, and the mixing weights. And so this step here is our Gibbs step. Secondly, we sample the random effects. This is the particle step. So in burn-in and adaptation, we propose a 50-50 mix of particles which come from either the population distribution or a Gaussian around the current random effect. From these proposal random effect particles and the current random effect particle, the particle with the highest marginal likelihood is selected, and this is done for each subject. We then update the current particle and random effect and repeat. Once we have at least enough particles to construct the conditional multivariate normal for each subject, we move into the sampling stage. In this stage, the majority of particles, 70%, come from the conditional multivariate normal, which is conditioned on previous good particles for each subject. This means that a higher percentage of good particles are sampled, with the safety net of some proposed particles coming from the group and current random effects distributions as well. In this stage, less particles are needed to be sampled, making it fast and efficient, whilst also giving those stable and reliable posterior samples that we need. For those interested in the maths behind the algorithm, here it is. This can also be viewed in the original paper, and I've provided a link for that in the YouTube comments. So there are several benefits of PMWG over other sampling methods, which include the efficiency of obtaining posterior samples. As you can see in this example, models tend to burn in fast. There's also no reliance on convergence. However, you can check convergence or something akin to that by simply repeating the method several times. The PMWG package also allows for easy parallelization across subjects, allows you to reduce the space of the sampling distribution for more complex models, and generally takes half the time or less than DMCMC. So the PMWG package is now available on CRAN, with necessary updates being released fairly regularly. To use the package, all that is needed is some data, which includes a subject column, some parameters to estimate, a log likelihood function, and some priors. The output returned includes all estimated components such as the parameters, the random effects, and the covariance matrix. As you provide the log likelihood function, this allows for complete control over what models you choose to estimate. The function should include 3 arguments, x, which is a vector of named input parameter values, the data, and a sample equals false argument, which is optional, but can be used in post-processing to sample from the posterior. Given these arguments, the function should return a single log likelihood value. This is the value that is used in the PMWG sampling algorithm to select the best particles on each iteration. And we provide some useful help to preparing your likelihood function in our accompanying documentation. The samplers team has also been doing some extensive work on preparing useful documentation to accompany the PMWG package. This is freely available and shows several worked examples with reusable code. We are continuing to update this resource, and we greatly appreciate any feedback. And a link to the documentation is shown here and can also be found in the YouTube comments section. Now I'm going to work through a short tutorial of how to use the package. This is a condensed version of a signal detection model that is fit in chapter 2 of our documentation. It's based on a lexical decision-making task. So first I load in my data and the libraries I need. I then specify the parameters that are going to be estimated. This SDT model includes 2 criterions, one for each proportion condition of the lexical decision-making experiment, where there's either more words or more non-words, and 3 D primes, one for each of the word frequency conditions, which were high frequency, low frequency, or very low frequency. In the likelihood function, I set the non-word distribution at 0, so these D prime values will give an estimate of the distance from non-word distribution to the 3 word frequency distributions. Next, I specify priors for the model, which here are broad, but you can specify your own depending on the model. Then I source my likelihood function. The function in this example uses pnorm to return probabilities for given responses across conditions, taking in the parameters that I have specified. It then returns the sum of these as the log likelihood. Next, I store these as a PMWG object ready for sampling. I then initialize the sampler, providing start points, but only if you want them. And then I run burn-in, adaptation, and sampling stages. So let's see how this all works now. I sped this up for convenience here, but note that the particle number and iterations are quite low for this easy to estimate model. And so there's guidance for these values that's provided in the documentation. Also note that epsilon automatically sets to 0.5. This is the value that controls the size of the sampling distribution. The acceptance rate here refers to the proportion of new particles selected on each iteration across subjects. And here we see the adaptation stage finishes early. This is good as it means we have enough unique particles to create the conditional multivariate normal for the final sampling stage, and then sampling finishes off the process. Before I finish up, I'd like to quickly go through an example paper that used PMWG and the outputs from this. I mentioned earlier that we can use the covariance matrix estimated by the sampler, and this is particularly useful in joint modelling applications, such as that done in a paper by Laura Wall from last year. I've linked this paper in the comments. In this paper, the authors compared participants across 3 simple decision-making tasks: a search task, a matching task, and a stop signal task, where there was 3 conditions of difficulty in each. The LBA, with varying threshold and drift, was fit to the data from each task with the likelihood functions all combined, such that each particle in the PMWG sampling method was a vector of parameters for all 3 tasks, which means for 9 parameters in each model, a 27 long parameter vector. This meant that the 3 models were estimated simultaneously with the off-diagonal of the covariance matrix, providing the most compelling results, as are shown here. In this correlation matrix, we can see the correlations between parameters across different tasks, which is really useful for interpreting underlying processes and their relationships across tasks and contexts. So this example is a joint model of several behavioral tasks, but you could also use this methodology to include models of neural or physiological data. So this concludes my intro to the PMWG sample package. Make sure you check out our sampler documentation, which covers all these topics below. And also keep an eye out for some upcoming posts on using the sampler for joint modeling, simulation, and recovery methods in the PMWG framework, and some other insights. If you have any questions or feedback, we'd love it if you reached out to us online or at the conference. Thanks.